In our previous video, we learned about chi-squared, and we saw how we could use it to test the goodness of fit for a particular solution. What I want to show you now is how we can use chi-squared to find the best fit to a possible solution. So I have some data here that I made up with x and y and an uncertainty sigma y. So I have 5 points, and I made up some y data, and I made up some sigmas, and you can see them plotted right here, and you can see their associated error bars. So here's x equals 1, and the value is 5 plus or minus 2, and x equals 2 plus or minus, and the value is 6 plus or minus 1, and so on. So now we want to see how we can use this to compute chi-squared. Oh, I even gave you a value of the theory, which I started off as 5. So let's compute chi-squared. So let's remember that chi-squared was delta y squared over sigma squared. So let's just say delta y, and let's compute delta y. So what's delta y? Delta y is equals y minus the theory, which is in D1, but we want to keep the theory fixed because we only have one value of the theory. So we say $d $1, and that is the theory value about 5. So if we copy this down, we can see that this works. So the value of the second one was 6, which is 1 greater, and the value of 4, which was 1 less, and so this is delta y. So chi-squared was delta y squared over sigma squared. So let's compute that, which is delta y squared over we'll call it sigma squared. Okay, we'll label it. So what is this? This is equal to this squared divided by this squared. And so we copy that down, and we can say that chi-squared is equal to just the sum of this. So we compute chi-squared for this particular thing, and we see that it is, we can get rid of a couple of decimal places here. Wrong way. Okay, we see that chi-squared is 17.44. And how many degrees of freedom do we have? Since I gave you the theory, and we have 5 independent measures, 5 points. So we could look up how probable is this fit with a chi-squared of 17.42 and 5 degrees of freedom. Well, fortunately, Excel has a nice function that lets us just calculate this. It's called chi-dist. So we can say that the probability is equal to chi-dist. You can see how the function appears if you click on it. And it's chi-dist of this, comma, the number of degrees of freedom, which in our case are 5. So we put that in, and we get a value which is 0.4%. So this data doesn't fit a theory of 5 very well. And you can see the reason why. The point that's giving us the trouble here is this point number 3 here, which has a small error bar and therefore a large chi-squared contribution. So its contribution to chi-squared is 11, where some of these other ones are small. Now we could play around with it and say, let's move the value down and put it at 4 and see what we get. So if we were to put the theory value at 4, chi-squared drops to 8, and we get a 14% chance that this is good. Not a bad fit, but you might ask, what's the best fit? And the best fit would be to minimize the value of chi-squared. So Excel makes it easy to minimize something, in this particular case, chi-squared. And we have a tool called the solver. And what the solver does is say, adjust a value to minimize another cell. So if we go up here to Tools, and we pull down here Solver, we get a window that says, set the objective. Well, in this case, the objective is this cell, which is chi-squared, and we would like to minimize it by changing, in this case, the theory value, which is for this cell. So we can simply say, let's put it over here, and simply say solve, and we go and we find the value chi-squared, let's remember, is 8.19 and a probability of 14% or 15%. If we say solve, it says, oh, if I make it 4.16, then I can go but lower chi-squared and keep a new value of probability, which is 16.6%. So if we cancel, we can see that we were at 14%, and so we weren't a bad guess before, but the solver actually allows us to minimize chi-squared. And so we'll do this again. We go Tools, Solver, and it still remembers what we want to do, which is cell we want to minimize. We say solve, and then we can say keep this value okay, and now we know that 4.16 is the best value of this. And just to remind you, if we were to compute the average value of y, let's just say average y, we would find that the average value of y equals average of 5, which is what our first guess was, and you can see that 4.16 minimizes chi-squared and therefore is the best fit. You can do this, by the way, with multiple areas. If you wanted to fit a slope and an intercept or multiple parameters, you can always use the solver to minimize several parameters to keep to minimize chi-squared with several parameters. This is really powerful because it doesn't matter how complicated a function you want to write down. If you can write down chi-squared and write down a set of parameters, the solver will minimize it for you to minimize chi-squared.